recording, share screen, share. And so today is HTML1. Yes? No? What two? Okay, there we go. So let's now look at last week's exercises I do yesterday. So what we were supposed to do there. Some of that was slightly messy. But the general idea, we're having increment 1, that's week 3. Yeah, so higher derivatives, and here's the solutions. I should upload the solutions to Moodle as well. Remind me if I forget that. So the question was that we have something moving on a path that's defined by this function. And what is the acceleration? And now physically speaking, if we have a location, x, then the first derivative of x is velocity, and the second derivative of x is acceleration. And the hint was that maybe we would like to shift that to be so that the S curve is at 0. So essentially we just drop the +6 from t, and then our new bounds are from -6 to +6. It gets to have, it's in a nicer form. So yeah, so the new domain is from -6 to 6, and then we start differentiating. The first thing is that when we're having a clear constant here, namely this 5, we're going to move it out. So now we have just the sigmoid function there that we need to differentiate. And now we're applying the quotient rule. Okay, so the numerator is 1. If we differentiate 1, then the derivative of the numerator is 0. The denominator is 1 plus e to the power of -t. And then the derivative of the denominator, this is g dash t, is minus e to the power of -t. So apply the quotient rule. We get the first derivative to e to the power of -t. So all we have, f dash is 0, so all we have left is f times g dash. F was 1, so g dash is minus e to the power of et. And then on the denominator, we do have, as per the rule, denominator squared. So that's the first derivative. Second derivative, actually, we have also shown that if we're having something in the form of 1 per f, the end result should be minus f dash. It's missing a minus somewhere here. No, there's minus. So minus f dash over f squared is the derivative of the inverse of a function. It's relatively well known, but we have just shown it to hold by the quotient rule. Okay, let's differentiate again. Now our numerator is e to the power of -t. So it has the derivative of minus e to the power of -t. And then our denominator, we need to apply the chain rule to get that. So we get -2 times e to -t times 1 plus e to -t as the derivative of the denominator. Apply the quotient rule again, we get that. And now you may notice that I have divided the quotient in 2, so we can divide it at plus or minus. So I have used exactly that. And now we have 2 times this over here. And we have 4 times it over here, so we can simplify that. And here we do have that once over here and 4 times over here, so we can slightly simplify that. One possible, there are different ways you can write this solution, but one simple way to write it is this should have a squared over here. So one way to write it is like this. So now what was missing, it did not have the 5 times which we had dropped off here. So I added the constant multiplier 5 there. And this is one way to put it. There are different forms. Some of you did keep the 5 there, so you got the 5 inside the formula. And if we consider reality, this so if it starts at rest, then and when it goes to rest, then of course rest friction is higher than moving friction. So in the physical case, we would probably have slightly different acceleration forces required. Okay, so that was just mechanical calculation, practicing a little bit on doing derivatives of the exponentials. Second problem, this is implicit differentiation. And yes, several people have brought this up that, hey, we could solve this analytically. Yeah, we totally could. One way of why we're doing this is that we could practice now solving that kind of a systems, because there are many times the underlying system might be too complex to solve. So one reason why we might use implicit differentiation is that we're having a complex system. SQL has systems where we cannot solve for P or Q. So now if we want to find out how does Q change if P changes, then we'll need to do implicit differentiation. And if we know that, and we're having some superior function, then if we know the tangent at some point, we could without calculating this more difficult function, well, that's a bit simple one we have on the practice problem, then we could use this tangent as an estimate where the value of the other function might be. There will be an error here. Typically, the further away, the larger the error. But that's one trick we can do to avoid calculating a hard function if we're kind of happy enough to have a little bit of error. In many engineering problems, the model itself is going to be simplification anyway, so it doesn't matter that much if we're having a little bit of extra error. And one typical problem is some kind of a supply and demand problem or a price and quantity sold problem. My first solution was slightly wrong, but yeah, we have revenue as PQ. We need to estimate how much Q changes for the change of P. Mathematically speaking, this is the dQ over dP. The equation is not separable, but we can differentiate implicitly. So we take d over dP both sides. And now I'm gonna do the basic problem solving principle of divide and conquer. So I don't want to do that all at once. I divide it at addition or subtraction. I'm going to divide it into parts. So the derivative by p of 2p squared is, well, okay, now I'm going internal side point by point. Okay, I'm going to take the constant 2 out. It's derivative of 2 times the derivative of p squared, which is 4p. Second term, we need to use multiplication rule because we're having p times q. And now, in case of implicit differentiation, the key idea is that we don't know how q changes with regards to p. So we're going to assume that it is just some function of p, and we're going to mark its differential with dq over dp. So p times q multiplication rule is that. The derivative of p, p times the derivative of q is p dq dp, and then the derivative of p with regards to p is 1. So we have just q there left, and it had a minus sign in front because we had a minus sign here. So we get minus p dq dp plus minus q. And then the final term, we need to use the chain rule because we're differentiating for p, and it is having p squared. Wait, there's a differentiating for q, there's a typo. So it's 2 times q squared. So I again took the constant out, and then chain rule is the outer function is something squared, which has the derivative of 2 times some function. The inner function is q, and times the derivative of the inner function is dq over dp. So we get 2 times 2q times dq dp, which is 4q dq dp. We collect the terms. Okay, the derivative of 200 is 0. So that was just a constant. We collect the terms, so we get this. We solve this implicit differentiation for dq over dp to get the change. So first, anything that doesn't have dq dp goes to the other side of the equal sign. We get dq dp, common term is minus p plus 4q equals q minus 4p, divide by minus p plus 4q, and we get this. I'm not sure if the cursor is visible on screen. So that way, okay. So that was how q changes when p changes. For the estimation step, we assume that this change is constant. So we assume what if this function was instead a straight line. So at the price of 2000, we have this kind of equation, and we solve for q, where we get the second degree equation, which has a generic solution of roughly 10 pieces, and a little bit more, but if we're selling full pieces, it's 10. So we get 2000. Okay, and we're having a really small difference, so it doesn't really affect, and certainly the change in the price seems to be quite small compared to that. So we can assume the change in quantity, which is officially we should use second here, but we're now going to, the estimation method uses tangent formula instead of the second formula, and change in p, we can calculate from what we had in the slides. So 5% change is 100 times delta p over p. So we can solve delta p from this, which is 5p over 200, which is 10 over 100 to 0.1 units. So we input this here, and 0.1 times a really small number is a really small number, so it doesn't really affect at all our sales if this function would hold true. So we expect to still sell 10 units, and if the model is correct, our revenue goes up by 5% with no effect on sales. So a key idea here is that we do use the implicit differential, which is used to find in formulas we cannot normally find the derivative of. We can still, using implicit derivation, we can find what is a change when one variable changes, then how does the other variable change? How many of you do remember something like partial derivatives? Okay, so That's going to be a bit later, but a similar idea present in a slightly different way for problems which have multiple dimensions. Then the antiderivative, so this is relatively simple. Well, acceleration is just the force divided by mass. So to find we want to find how does the location behave. The first integral is of acceleration is velocity. I'm gonna now put the mass out, pull the mass out of here, and I'm also, there's a common constant of 16. I'm gonna pull that out as well. And now, after we remove the constants, this is relatively easy to integrate. It has an integral of so the constant 16/75 times minus t cubed divided by 3 plus 16t plus some constant. Remember to keep that there. And this constant now stands for, in the velocity function, this stands for what the velocity is when our time is 0, which in this case wasn't actually, so we were going from -4 to 4, so it's on the center of the impulse, not at the beginning of the simulation. And then to get location, we integrate the velocity, so we get this. Do note that the integration ends here, so we get the integration of minus t. Wait, this is something funny. Yeah, actually, this is slightly wrong. I should have a dt here. And another integral sign here. Otherwise, we cannot take the common term out. So we're having this, and we're going to divide it at the plus. So this is just the second integral, but then we need to integrate also the constant v1. And we also get to add some constant x1, which stands for what is the location of the part at x1, at the time is 0. And then after we're done the integration, so take the antiderivative of that, we should get something. And now I'm gonna multiply everything by 16 there, so we should get this kind of a equation. And now when we did not begin at rest or begin at t equals 0, rather than v1 and x1 are not the values at the beginning, but instead at t0, and our stuff started at t equals -4. Okay, so relatively mechanical stuff, but just trying to have an example that instead of y's and x's, typically our variables stand for something. Also, this week's problem 2 had some discussion that how do we find those. So problem 1, some people had both yesterday and today a bit trouble on finding A and B. So now that requires some knowledge of electronics. So on an electric circuit, well, with DC circuits, then now our coil is a component that has a little bit of delay until the circuit reaches equilibrium. So it's gonna go towards resistor defined value of U over R. It's gonna start from 0 and it's gonna approach asymptotically. And from the generic solution of the differential equation, we should be able to read that it does approach those values exponentially. Or well, it's probably going to have a minus somewhere on the power. So exponential power minus 1 defines how much difference we have, and it's going to go to 0 when time advances. So that's a little additional hints on problem number 1. Problem number 2. Now we do not have a known damping term, but you can start checking what it looks like. And we have 3 different cases for differential equations. And one case is standing for oscillations, one case is for critical damping, and one case is for overdamping. You should be able to figure out that now that we have a known mass and known spring constant, then you should figure out that which values of the damping constant do essential dampener stiffness, which values do correspond to which case. So one question was that what is the physical interpretation of each of those cases if our differential equation is modeling a vibrating mass. There's a few videos on Moodle which are going to be helpful for this. And then when you know which case corresponds to critical damping, you know then what the derivative value must be at or must be like at that case, and then based on that you should be able to solve the damping factor by putting the mass, spring constant, and unknown B, so unknown damping factor, into the formula of the discriminant. Okay. Anyone having any questions on this week's exercises at this point? No? Anyone still awake? Everyone still awake? Someone at least saying no? Well, let's see. We had one piece of theory that was something I had in the original schedule that it's this week. Which is hyperbolic functions. And this is now, after reviewing the material, I think that maybe it is a bit too early. But but not necessarily, because some people did actually get a hyperbolic solution to last week's questions, and there is a connection between those exponentials and hyperbolic functions as well. But you will usually run into these when we're doing antiderivatives. So you may remember that the derivative of sine is cosine, and then derivative of cosine is minus sine, and so on for other tangents and so on. Then how the inverse functions. So we needed to do stuff like that. Limits. This is a correct one. Yeah, so actually trigonometric functions are apparently the same, so we can find, and we do note that the domains are, so when we pick just to have, now we're going to make these restricted functions on the sign so that it is invertible. So otherwise we cannot find an inverse function to trigonometric function, because the inverse function would not be a function because it's a cyclic one, so it repeats. So now when we take just one wavelength, we can invert the function. So for example, what does sine look? What does this capital S sin look like? I'm gonna run MATLAB. Hopefully it's gonna start today. big question is, am I into? Yes, I'm in the internal network. Yes. If you install MATLAB from the student license we have available, it will run on, well, anywhere, but the staff license one requires that we are inside the university network. It will call home. Okay, so let's have x equals linspace minus pi over 2 to pi over 2, and let's say something like 100 points. Yeah, that's going to be enough. And now we're going to plot x and sin x. So I'm just using this to draw. So what we're looking at here, the restricted sin, now it becomes invertible because we're having just one slope. So this is now growing. And now it is monotonically growing, it is invertible function. And the inverse of that, well, we notice that the capital sin goes from 1 to 1, minus 1 to 1, so the domain of the inverse is 10 from minus 1 to 1. We can do similar things for the cosine and the tangent. And now when we start doing the derivatives of these inverse functions, we get this kind of a values. And you may occasionally figure out that we need to deal with functions that look like this. And then if you're integrating a function like that, you're going to get the Arcus function as an integral. So this is where you might occasionally run into. So if you have some kind of variable that changes to, for example, roughly 1 plus x squared, and you need to integrate an inverse, then you're going to get that your integral is going to be an Arcus tangent. And now there are, well, we may remember there's a connection between the unit circle and sine and cosine. So if we're having angle x, then at that angle, the point on the unit circle is going to be let's see how soon I'm gonna mess up one of these markers on my own markers. So when we have a circle with a center on the origin, radius of 1, 10 at some angle alpha, the point is going to be cosine alpha, sine alpha. And now we're going to have hyperbolic functions. If this constant c is 1, the connection is that now that we're having x and y and hyperbola, which has the function, well, this is not really a function, but has the form of x squared minus y squared equals 1, then a point on angle alpha at the hyperbola is going to be hyperbolic cosine alpha, hyperbolic sine alpha. One thing what we can clearly see, the hyperbolic cosine, which has the x coordinate, can never be smaller than 1. Same as cosine will never get values values greater than, or sine will never get values greater than 1 because there's a unit circle here. So, and also there's a different form. So why you got those hyperbolic functions in the derivative on last week's part is that we do have an alternative form to say what is the value of the hyperbolic cosine, and then we have a corresponding. If it is even, then we have an odd function which does also have a interpretation by exponentials. And just like we have this property that cosine squared t plus sin squared t is 1, there's a similar property for hyperbolic cosines and sines. Also, there's a nice property that the area under alpha, when we're using radians, is a sector on the unit circle is alpha by 2, and also on the between the y-axis and that angle and x-axis we get alpha over 2 if alpha is radians on the unit hyperbole. Derivatives, okay, we can calculate these derivatives relatively easy by falling back on the exponential form. So we find out that the derivative of hyperbolic sine is the hyperbolic cosine, and vice versa. So if you remember that, okay, in regular cosine have minus sign, so there is a flip here, but it's inside the function, and by the interpretation, there's no flipping sign on either of those. So the sign change is in the exponential form. Then we can also define a hyperbolic tangent, which is just like a normal tangent is a sine over cosine, and the hyperbolic tangent is hyperbolic sine over hyperbolic cosine. Cotangent is the inverse of that, so going the other way, and then secant and cosecant. And we could then similarly expand those to exponential forms and use those forms to differentiate these functions. I have skipped the differential forms and just have the formulas here. But if you do the work, you should find using a quotient rule what these are. And then the big question: why on earth would we need to learn those? Well, let's first have a look at the inverse. So, okay, inverse functions look like that. So we had exponentials, so we do expect that we're going to find logarithms here. And you know the domain. So indeed, the cosine, hyperbolic cosine values are never smaller than 1. So the domain of the inverse must be greater than 1, and so on. We'll also say here that if this is real, then x cannot be too close to 0. So, and then was the part of what are they needed for? Well, one thing is that the hyperbolic cosine has an interesting property of having minimal energy. Does anyone wear a necklace? Kauanauha. Yeah, okay. So, okay, if you had no additional weight on it, the chain would be a hyperbolic cosine. So called catenary curve. So catenaria means chain in Latin. And that's probably one of the only pieces of Latin you're going to learn in this school. The soap bubble also being, what kind of a shape that if you blow a soap bubble, what kind of a shape it will take is actually actually a catenary curve that rotates around the central axis. And of course, if we had just a moment ago what the derivatives looked like on the inverse different functions, and these are slightly different variables. If you're seeing this kind of functions, you need to integrate. Then the integrals are going to be hyperbolic trigonometric functions. In some cases, we don't readily have direct these forms, but for example, if we replace, so do a substitution, then we can easily get that kind of a form. And practical applications, we have a little specialty in LUT. This is the only university in Finland that teaches nuclear engineers. Anyone wanting to work with nukes? Okay. Orange transformations in interior of relativity end up having a possible representation with the hyperbolic functions. Anyone working with the reactors, if you want to figure out how a reactor goes, and for example, in a power plant, then shockwave fronts, reaction diffusion fronts, and so on end up being hyperbolic functions. And of course, some of you noticed already on the previous week's exercises that the sigmoid function had possible representation by hyperbolic functions. And if I'm on time, well, okay, I was a bit quick, but that's what material I had tonight. If you have any questions on the exercises, you can ask. This is gonna take a while. I'm gonna stop the presentation and trying to save this as a video. And I'll try to get tomorrow these videos on Moodle because the law has recently changed. I need to, if I'm doing inside the EU, if I'm doing videos in English, those need to have subtitles. So I need to make subtitles now because that's required of public institutions. And